Hi, welcome back for part 2. For this one we're going to start by looking at the reflection from the y-axis now. Before it was from the x-axis when the negative was outside of the bracket. Now we're going to look at when the negative is inside the bracket. Here b is negative, or sometimes we can write it like this: f of a negative x there, where every x is replaced with a negative x. So this one, this graph has been reflected in the y-axis, so the new graph will be a mirror image from left to right when compared to the original. So for example, if I've got the square root function, y equals square root of negative x, then b is actually in negative 1. So this one is a reflection in the y-axis. In this case, each x value has been multiplied by negative 1. Flipping the graph from left to right, as you can see over here, this point is now like that. This point is now over here. This point is now over here, so on and so forth. Hopefully they're straight lines, not like my dodgy lines there. Anyway, example 8. In this case, we're going to have a look at this one. Square root of negative x squared, all in brackets. So again, b is negative 1. So this is a reflection in the in the y-axis. But note that the graph doesn't appear to change in any way, because this point is now over here, this point is now over here. So it looks identical, but it is in fact reflected in the x-axis. Sometimes with reflections, you can reflect them in the x-axis this way, and you'll see no difference. Sometimes you'll reflect them in the y-axis, and you'll see no difference. But we still go through those same transformations, still label them exactly the same. So now we're going to have a look at some translations, moving the graph left and right, up and down. So I'm going to look at first at h. The two variables will be h and k, but I'm going to look first at h. Now, sometimes people can get a little bit confused by this, because I do it a particular way and you might do it slightly differently. As long as you're consistently getting the right answer on these, it doesn't really bother me too much how you go about it. But I like to have it as x minus h, all to the power of n, or the other way of looking at it is f of x minus h. So every x value has been replaced with x minus h. So the graph can be moved left or right by a factor of h units parallel to the x-axis. That seems a bit counterintuitive. Parallel to the x-axis, you feel like that one should be moved up and down, this way. But in fact, parallel to this axis would actually be along this way. Okay, so parallel to the axis is actually left and right. If h is, this is where people get a little bit confused. If h is positive, the graph is moved right. If h is negative, the graph is moved left. I guess what I'm really saying is, if it's x minus 2, then the graph has been moved 2 to the right. So in this case, h is actually 2, because I started with x minus h. Again, if you're getting them all right, then you don't need to worry too much about this. But the graph has been translated 2 units to the right. Okay. In this case, because it's a truncus, the asymptote has been moved 2 units to the right. I mean, everything has been moved 2 units to the right, but the thing that we notice the most is that the asymptote has been moved. The x-asymptote has been moved 2 units to the right. So again, we're going to have a look at another one. This time it's x plus 1. So in this case, h equals negative 1, given that we started with x minus h up here. But again, if you can just look at that and notice that that should be translated 1 unit to the left, then I'm happy. The turning point, or probably point of inflection, would be better than turning point for this graph, because it's a cubic point of inflection. I can't write and talk at the same time. The point of inflection has been moved 1 unit to the left. Okay, so that's what happens when you move it left and right. Fairly straightforward. Hopefully you've seen all of this stuff before, but particularly that. This time we're going to change the k, so this is the other translation. So it'll be x to the power of n plus k, or all minus k. Sorry, plus k, but k can be either negative or positive, as I've got it written in there. Or f of x, so the original graph, plus k. So the graph can be moved up or down by a factor of k units parallel to the y-axis. Again, that is a bit tricky, but there's the y-axis, and if you're going to move parallel to that, you would move up and down, not left and right. So if k is positive, the graph is moved up. If k is negative, the graph is moved down. So again, I'm going to start with a hyperbola, 1 on x minus 2, where k is in fact negative 2. The graph has been translated 2 units down. Okay, so for hyperbolas, it means that the asymptote has been translated 2 units down, parallel to the y-axis. Okay. Let's have a look at this one here, where we've got the square root of x, and this we're going to do square root of x plus 3. So in this case, k is 3. Sure. Yep, I got the other one right too. So the graph has been translated 3 units up. So for us, the easiest thing to look at is the end point. It's all points, but for us, it's easy to look at the end point. Has been translated 3 units up, parallel to the y-axis. Okay, so that gets us to the end of the transformation. So just really quick recap. Where are we? On our first page, we've got AFX, both the dilations and reflections. First of all, it can dilate it from the x-axis or reflect it in the x-axis. B dilates it from the y-axis or or reflects it in the y-axis. H moves it up and down, left to right. We're going to have a look at multiple transformations now, so when lots of things can be applied to the graph together. So we're going to just have a look at some random questions. This one here, y equals 2x squared minus 1. I always like to write it like this, even though it seems a bit tedious for this one, but I always like to write it like this, x minus 0 squared. Actually, I'll probably add another layer to that. Even though it'll look unnecessary for this one, it'll help later on. B, which is 1, x minus 0 squared minus 1. Okay, just writing that in the standard form like we had at the front, probably unnecessary for this one, but I like to do it. So here I can see that it's been dilated by a factor of 2 from the x-axis, looking a bit squishy there. And it's also it hasn't been translated. It hasn't been reflected in either axis, and it hasn't been dilated by a factor from the y-axis. It hasn't been translated horizontally, but it has been translated vertically. A translation of 1 unit down. And it's good to know the domain and range as well. I mean, it's fairly easy to see because of the graph, but the domain is all real numbers, and the range. In this case, the turning point is actually down at -1, so the range will be from -1 and including -1 all the way up to infinity, although not including infinity. It's an interesting question. Can you actually get to infinity? Probably not. Anyway, something for another time. Let's have a look at the next one. Again, I always write it in this form because I can see it much easier this way. Maybe you're more intelligent than me and you can see it straight up, but I find it a little bit trickier, particularly with questions later on. So I write them always like things that I know. There's nothing stopping you doing that. There's nothing stopping you changing, the question so that it works for you. Obviously, you still have to answer their question, but you can do it, going a variety of ways. Translation. This one will be a translation of. There's 2 different ones. 3 units right and 1 unit down. Okay, so for this graph, it's really the end point is the thing that we'll have a look at the most. The end point's been moved 3 right and 1 up. Not down at all, is it? You probably already saw that. Up. plus 1, so therefore it goes up. My mistake. So it goes 3 across and 1 up. Luckily I've got the graph there that I can look at. So the domain for this one is, the domain used to be from 0 to infinity, and now it's going to be from 3 to infinity. And the range, well, the range used to be from 0 to infinity again, but the range now starts at, it's including that point 2. The range includes 1 and goes up to infinity. Okay, let's have a look at the next one, and this is particularly where I start to say, insist on putting it in the, my format, because otherwise people will think that it's been moved differently than it actually has. So if you write it like I write it, so that I take out my common factor of 2 and I write it as x, I always want 1x there. Excuse me. So I go back to my standard form of a b x minus h to the power of n plus k. That's written in that form. If I do that, I'll virtually never make a mistake. It's only when I start to try and do too many things in my head. So this one's been dilated by a factor of 2 from the not correct, sorry, a factor of 1 on 2 from the y-axis. Okay, and I'll come back to the other type of dilation it could be, but we'll do that in just a second. Okay, and as you can also see, it's been translated 2 units left and 3 units up as well. So the domain, we'll have a look at that first. If it's been translated 2 units left, that means that it is all real numbers except for the number -2. Alright, not very good writing, but there we go. Okay, there's other ways to write that, but that's certainly one of them. And the range is all of the numbers bigger than 3. Okay, so from 3 to infinity. Now I mentioned before that this actually could be a different dilation as well. It's true. I might just do a little bit of scribble over here, and I'll leave you to it. So that is 1 over 2x plus 2 squared plus 3. That can also be written as 1 over 4x plus 2 to the power of 2 plus 3. I've taken the 2 out as a common factor. Sorry, I've taken the 2 outside of the bracket. I've squared the 2. You can't always do that, but in this case I can do that. Sometimes, if it was a sine graph or a cos graph, you can't actually drag the number outside the sign, or sometimes if it's other tricky things, like if it's to the cubed root. I mean, I guess you could do it, but it just gets a little bit trickier. But in this case, it's very easy. So that would actually be a dilation. It could also be a dilation of 1 on 4 from the x-axis. Okay, so yeah, it can be a little bit trickier. Both the answers would be accepted if it was written like this, but I guess the more obvious one is that it's a half from the y-axis. Okay, the next question. This one again. This is why I'm going to insist that you put it in my form, because it just, I couldn't do all that in my head. It just gets too hard. Once you put it in my form, it's really easy, because you just read off it's dilated by a factor of 3 from the x-axis, dilated by a factor of 1 on 2 from the y-axis, translated a half units left, and translated 2 units down. Okay. When we were drawing it, we probably didn't go through all of that in our head, but that's the language of what's actually happened to this graph. The domain and range are fairly straightforward. It's just real numbers for both of them. Now, this is what I was mentioning before, that you can actually have 2 different types of dilations. Like I had, dilation from the x-axis, dilation from the y-axis. You can actually just make it one dilation if you follow all of this yucky algebra, all these numbers here. You can actually take the 2 outside of the cubed root bracket, it ends up being 24. So it could just be dilated by a factor of 24 from the x-axis. That's possible as